So we have seen that the pseudo-residual, we have used the pseudo-residual and we've shown that it is very similar to the residual for squared laws, right? For squared laws. This is what we have already shown in the video above. The question here is a very interesting question, which is the pseudo-residual. What is pseudo-residual? If you have a loss function L, right? Your pseudo-residual is derivative of the loss function with respect to your function K. Is this equivalent to, or is it very similar to, very similar to residuals or errors for non-squared laws, functions, right? Remember, what did we show? We showed that if my loss function is squared laws, we've shown that this is equal to 2 times yi minus fkxi. We've shown this, and this is like your error, right? But we showed this only in the case of squared laws. When we used a simple regression, when we used a regression example, right? And when we use squared laws, the question gets interesting now. What if you have a loss? So instead of regression, what if you're performing classification? And what if instead of squared laws, you have another loss? Like let's say you're performing a binary classification task, and let's assume the loss that you have is a binary log loss, right? Then does the negative of the gradient or the pseudo residual, is it still same or similar to residual or error, right? So that's a question we'll try to answer. So first let's compute what is derivative of L with respect to derivative of fkx, right? This is what we'll try to compute. And I can write my fkx as yi hat, right? Because this function is giving me a yi hat. So let's look at a couple of examples, and we know what binary log loss is, right? So there's a very nice Wikipedia example. There's a very nice example on Stack Overflow, not on Wikipedia. This article simply has, if you just Google search for gradient for logistic loss function, you get it. And this question has been answered very well in the context of boosting, right? So let's assume I have a loss function like this. This is my binary log loss, right? We have seen this multiple times. If I have two classes, this is what my binary log loss looks like. And what is pi here? Pi here is 1 by 1 plus e power minus yi hat, right? This is what my pi, this pi here means this. Very, very simple. Just take a look at this. This is your binary log loss, and this is what your probability value means. If you remember from your logistic regression discussion, this is your logistic function, right? This is nothing but 1 by 1 plus e power or exp of minus w transpose xi yi, right? Minus w transpose xi, right? Because this is your yi hat, isn't it? This is your logistic function. This is basically logit of w transpose xi, right? This is nothing but the logistic function, and that gives you the probability of the ith point belonging to class 1. Okay, now you can rewrite this above equation as this. You can rewrite, basically I'm replacing the pi value here. The pi equation that I have here, I'm just replacing it here, and I'm also replacing it here. Right? Once you replace it here, if you perform 1 minus this, you get this. So straightforward algebra, nothing very fancy here. Now comes the fun part. This is what you have, right? Now if you take the derivative of L with respect to yi hat, so this is nothing but derivative of L, which is written as L dash, right? Derivative of L with respect to yi hat. What is your yi hat? Your yi hat is nothing but fk of x, right? If you perform your derivative, what you get is this. And you can easily get this by simply performing, I mean, of course, in this example, it's shown that it's performed using a software tool called Wolfram Alpha, but you can just apply chain rule. You can simply apply chain rule of differentiation, and with some algebraic transformations, the derivative of L can be shown to be equivalent to this. Please take that as a simple assignment. It just requires some patience, and if you just apply chain rule carefully, you can go from here to here. Now, once I have that, this is the fun part, right? Once I have this, once I have my L dash as this, if I multiply both numerator and denominator by e power minus yi hat and e power, so you're basically multiplying it by 1, right? You're basically multiplying both numerator and denominator by the same value. Once you do that, your L dash or your derivative is equal to this. And with some simplification, with some algebraic simplification, you can show that your derivative is yi minus pi, right? So when you have a log loss, when you have a binary classification task, and when your loss is log loss, your negative of derivative with respect to fkx is equivalent to, right, is equivalent to, so you have to take the negative of this, which becomes pi minus yi is equivalent to pi minus yi, where pi is equal to, this is important, what is pi here? 1 by 1 plus exponent of minus yi hat. And what is yi hat here? Right, your yi hat is nothing but 1 by 1 plus exp of minus fk of x. Right? So you can think of this pi as the probability of your ith point, your xi, belonging to class 1. The simple probabilistic interpretation of binary classification. And we have seen this multiple times. We have seen this in logistic regression a lot of times. So in a nutshell, the negative of the derivative that you got, is equivalent to the probability of the ith point belonging to class 1 minus yi. Right? Let's think about it. Let's assume, so this is actually, if you think about this, remember what are your yi's? Your yi is basically 0 or 1. Your probability values, this is basically probability of xi belonging to class 1. Right? So you can think of this as an error. See, this is your pseudo-residual. This is your pseudo-residual. And this is like an error or a residual. Because this says how inaccurate is my probability estimate of P belonging to class 1 and what is the actual class label itself. Right? So this is, if you think about it, this is very, very similar to your yi minus fk of xi in the simple squared loss case. In the squared loss case, this is the actual value, this is the estimated value. You have this subtraction of one from other, and or you can think of this as yi minus yi hat. This is what you have in the case of squared loss. In the case of log loss, you have something very similar, not exactly the same. Right? You have something very similar. So even in the case of a binary classification task, you can take the pseudo-residual or the negative of the gradient of L with respect to fk. You can think of it as an error or residual. But there's a big case here. Just because you can always think of your pseudo-residual, so let's take the next extension question to this is, can pseudo-residual be always interpreted as a residual or error? Is pseudo-residual always? Right? We have seen that for squared loss, yes. Right? Even for log loss that we have just discussed in this video, the answer is yes. But if you have some other loss, so for any loss, is the answer yes? No. That's a big no. Because it's not always true that a pseudo-residual can be interpreted as a residual or error. Because your loss function is any differentiable loss. So in the case of gradient boosting, right, that we will learn shortly, if L is any differentiable loss, it will be hard to interpret in some cases. If you have any loss, I cannot interpret my pseudo-residual as residual or error. Not always. That's the important thing. So in the case of squared laws and log laws, which again, squared laws is what we use a lot in regression, and log laws is what we use a lot in classification, right? So in these two cases, yes, there is a very neat interpretation, but not always, because L could be any differentiable loss function, right? That's a very, very important thing. Now you might wonder if the answer for any L is no, why are we, so this is the big question. Why are we using pseudo residuals? Why are we using pseudo residuals? Why are we even using pseudo residuals? Which is nothing but your derivative of L with respect to Fk of x. Why are we even using it? Why can't we just use the residual directly? So the answer to this question is slightly deep, right? I also have a video in the same section where I'll explain the deeper mathematical intuition on why we use pseudo residuals from a pure optimization standpoint, right? So what we've seen till now, like using pseudo residual or considering pseudo residual as a proxy to residual, is just a simplifying technique for us to grasp this concept better. But the more deeper fundamental mathematical concept, mathematical reasoning and proof for using pseudo residuals is something that we will discuss in the next video.